Hey, my name is Milan, and in today's video, I'll show you how to implement semantic search using MongoDB Atlas Vector Search. Semantic search can be a significant improvement compared to keyword-based search when we aren't sure what exactly we are looking for. It's searching based on meaning instead of looking for a specific term. We have a lot of concepts to cover in this video, like setting up vector search, generating embeddings, and implementing semantic search inside of a .NET application. So let's dive in. So as I said, I'm going to use MongoDB, who is also the sponsor of today's video, to implement support for semantic search inside of our .NET application. Now, you may know MongoDB as a document database, and that's for a good reason. It's the #1 most popular document database in the world. However, it can also work as a full-featured vector database, and this is what we're going to leverage to implement semantic search. And when you think about it, this is a very powerful capability of MongoDB. We can use one database to store both our application data as documents inside of the database, as well as our vector embeddings that allow us to perform vector search. But first, let's take a step back and try to understand what vector search is and how it actually works. The first concept that you have to understand is a vector embedding. A vector is just an array of floating point numbers, and a vector embedding is a numeric representation consisting of these floating point numbers of a semantic concept, including its data and the related context. Now, what you see here is just a three-dimensional representation of some vector space, and each point in this space represents a concept. Now, what vector embeddings allow us to do is to compare different vectors and determine if they are numerically similar. For example, the concepts of a tiger, a lion, and a bobcat could have similar vector embeddings, so they're going to be close by in this vector space. And we can perform vector search on these vector embeddings to determine the distance between them, and we can translate this into a similarity comparison. So what we can do next is perform a so-called vector search, where we specify our search term, convert it into a vector embedding, and compare it to the vector embeddings that we have inside of our vector database. Now, in our case, we won't need to use a specialized vector database, and instead we can use MongoDB Atlas. What we are going to implement in order to add support for semantic search inside of our .NET application is two distinct flows. The first one is going to be taking our content, which are going to be our documents inside of MongoDB, and running them through an embedding generator. This is going to produce a vector embedding, which, as I said, is just an array of floating point numbers that we are going to store inside of our vector database. Now, remember that we don't need a specialized vector database, and we can leverage MongoDB to also store our vector embeddings and then allow us to perform vector search. And this is the second flow that we have to implement, which is our application sending a query, a search, if you will. And what we do is also run this search term through the same embedding generator. And this is very important because we have to produce a vector embedding of the same number of dimensions to be able to perform the vector search. Now, this is going to vary based on which large language model you are using to produce the embedding, but we're going to discuss this more when we get to the practical part of this video. So then, after we have produced our vector embedding for our query, we can send it to Atlas Vector Search to perform the actual vector search, and this will give us back our documents ranked by the relevance or similarity to the vector embedding that we sent as a query. So you can see that MongoDB Atlas Vector Search offers many benefits, the most important one being semantic understanding of the query that we are trying to perform. This means that our search term can carry meaning. For example, instead of querying for a movie where the plot contains Wild West, we can search for a movie that contains cowboys and horses. Then we can convert this into a vector embedding and use Atlas Vector Search to return movies that are the closest match to our semantic search. We also get scalability. MongoDB Atlas works across all of the popular cloud platforms, including Azure, AWS, and Google Cloud, and it's optimized for working with large datasets. Now, there's also the concept of search nodes if you really want to scale your vector search capabilities, and I'm going to discuss this more in just a moment. Another benefit that we get is flexibility. We can use any type of content to perform vector search so long as we can convert it into a vector embedding, and this can be text, image, audio, or video content. Now, in the previous point, when I was discussing scalability, I mentioned search nodes. And how you typically deploy a MongoDB Atlas cluster is we have our database and our vector search capabilities running on the same node. And this prevents us from scaling our search capabilities independently, which is why we can move search into a so-called search node. This gives us the ability to scale the database aspect and the search capabilities independently depending on the requirements of our application, and this in turn will give us better query performance. So MongoDB is really powerful in this regard, and it can really grow according to your business needs. Now let's jump into the code and let me show you the demo application that we're going to extend to implement support for semantic search. Here is our demo application that currently only supports simple keyword-based search. We have one API endpoint with the route of API/movies, and it uses a movie service abstraction, which it obtains through dependency injection, to call the getMoviesAsync method. This accepts a term and a limit query parameter, with the default value being 10 movies that we can return from our API. Now, a couple of other things that we have is configuring the iMongo client by providing the connection string, and I have this available because I already installed the official MongoDB driver. This is what I'll be using to query my MongoDB database and also to execute vector search when we implement support for this. So all I need to do is initialize a new Mongo client and provided the connection string. I'm going to show you how to obtain the connection string in just a moment when we take a look at MongoDB Atlas. Now, one more thing I want to show you is the actual movie service, where I'm injecting the Mongo client that I configured with dependency injection, and I'm using it to access my database. The database name is sample_mplix, and it's a sample database that you can load inside of your MongoDB Atlas instance to have some initial data to work with. After I obtain my database, I can get my collection, and I have a type here called movie representing the documents inside of this collection, and the collection name is embedded movies. I'm going to show you the contents of this collection in just a moment, and the reason I'm using this collection is because it contains fewer movies and it's going to be slightly simpler for this demonstration, especially when we get to the part where we have to generate the embeddings for our movies. Now, the actual implementation for fetching the movies is quite simple. We are just initializing an empty filter, and if the search term isn't empty, we are updating the filter to convert the movie's title into lowercase and then do a contains query based on the search term. And then I can use my collection to apply the filter, limit the search results, and then materialize everything into memory before returning it from my API. Now let's actually start the application, and then let me show you the client application. It's just a simple HTML file that's using Tailwind CSS for stylization and plain JavaScript for implementing the functionality. Now, the main functionality is inside of the search movies function, which is going to grab the search term that we input and is going to call our API running locally and pass the search term using the respective query parameter, and then it's going to load the results. I'm going to serve this using a local HTTP server, so now I can navigate to my client application, and by default I'm going to be greeted with an empty screen. So if I press search, we're going to execute our empty filter, if you recall, and we are going to get back 10 movies from our MongoDB instance. Now I can of course filter this. For example, if I enter Batman, it's going to apply keyword-based search looking at the title, and as long as the title of the movie contains our search term, we should see the respective movie in the API response. Now this is all great if you want to do keyword-based search, which is also a built-in feature in MongoDB Atlas, just like vector search. But if I were to search for a wild western with cowboys and Native Americans, and I clicked the search button, you will see that we don't get any response back from our API, and this is because keyword-based search doesn't understand the semantic context of our search term. Now, in order to fix this, we need to add support for vector search inside of our MongoDB Atlas instance. If you navigate to your MongoDB Atlas dashboard, you'll be able to set up your cluster. Now, I already created my cluster. It's called the Vector Search cluster, and inside of it, I introduced my sample data. If I go into Data Explorer, I can see the one database I have inside called sample_mplix. Now, if you don't have the sample_mplix database inside of your system, I'm going to show you how you can create it. If you navigate back to the clusters view, you can click on the three dots here next to your cluster and click on the Load Sample Dataset button. This is going to offer a couple of sample datasets that you can load into your database, and from here I'm just going to choose sample_mplix, and I'm going to say load sample data. And if I don't have this data set inside of my database, it's going to be created. Now this can take a couple of moments, so I won't make you wait, and I'll jump into the future when my data set is ready. After a few minutes, you should see that your sample data set was successfully loaded. If you are wondering how to get the connection string for your MongoDB instance, you can click on the connect button here, and this will give you a couple of options for choosing your connection strings. For our use case, you want to choose the drivers as the connection method and then pick the specific driver that you will be using. We will be using the .NET driver, so we have to install the respective package inside of our application. We've already done this, and then you can find the connection string here, which you can copy and add to your app settings. Now you will have to update the database password based on the user that you have selected in the dropdown. I only have one user, and I'm going to include this using my application secrets so that I don't accidentally expose it in my source control. Now let's go back to the dashboard. So you can go ahead and click Browse Collections, and it's going to take you back to the same screen that I showed before, containing our sample Mplix database. Now if you recall, we had two similar looking collections inside, movies and embedded movies. The difference between the two is that the embedded movies collection already contains a vector embedding inside of our documents. So if I navigate to the first document here, I can see the plot embedding field, and you can see it contains an array of numbers representing our vector embeddings. Now this specific document contains 1,536 vector embeddings, and this was generated using an OpenAI model. What I'm going to be using is a large language model that I can run locally, and for this I'm going to use Ollama. Now the next thing we have to do inside of our database is navigate to data and then go into search and vector search, and this is how we can actually set up support for vector search. Now this actually uses an index, and you can go ahead and click the create search index button, and you'll be offered between two different types of indexes. There is the Atlas Search index, which allows you to perform full text search on your collections. However, we are interested in vector search, which allows us to perform semantic search inside of our applications. Now, what's very interesting is that you can perform what's called a hybrid search, where you can combine the results from a vector search and a full text search to improve the relevance of your search results. Now, this is a bit out of scope for this video, but I want you to have it on your radar, so I'm going to leave a link to the documentation in the description of this video. Now, how do we actually create our vector index? Well, we have to give it a name, and I'm happy with the default name. I can choose the collection that I want to index on, and I'm going to look for embedded movies because it contains a slightly smaller data set and is going to be simpler to generate the embeddings. Now you have two options for configuring vector search. You can use the visual editor, which is very simple to use and you don't have to write any code, or you can use the raw JSON editor where you can customize the index definition. Now I'm going to demonstrate both of them, starting with the visual editor, and you can see it's pretty simple. We just have to choose what is the vector field that we want to use for vector search. Now in our case, there is only one field containing our vector embeddings, which is the plot embedding field, and the number of dimensions is a fixed number and is going to be 1,536. Now the next thing you have to choose is the similarity method, which is how we are going to calculate how similar two vectors are when performing vector search. There are three methods that you can choose from: dot product, Euclidean, and cosine. And for example, I'm going to choose the dot product. However, you can also take a look at some documentation here to see how do you pick the right similarity method. One more advanced feature that you can configure is the quantization option, and this allows you to shrink the amount of memory that your vector embeddings take, and this improves performance by reducing resource consumption, and it also allows you to store more vectors in the same amount of memory. So consider this if you are working with a very large number of vector embeddings. For my use case, this isn't really required, so I won't be using it. Now, another interesting thing that you can configure in your vector search index is your filter fields, and this can help you pre-filter your data before performing the actual vector search, which is computationally expensive. So for example, I can pick a path. Let's say I want to filter based on the year, and by including this field, I can use it inside of my query as an additional filter before I perform the vector search. If I'm happy with all of this, I can click Next. This is going to give me a brief summary of my vector search index, and then I can click Create Vector Search Index. Now I mentioned that we can also configure this using JSON, and this is what the JSON representation looks like. It contains the fields that are part of our index definition. The first field is the plot embedding field with the respective number of dimensions and the similarity method that we want to use when performing vector search. And of course, the type of this field is a vector. Now we can also have a filter field, which in our case is just going to be year. Now I'm going to copy this and close this down, and let's go back to our search indexes, and I'm going to start over the process from scratch using the embedded movies collection and the JSON editor. So let me click next, and I'm going to paste in what I copied from the previous step because I want to customize it. I want to use a different field for my vector search. I'm going to call it plot embedding 1024, and this is because I want to use a different large language model for generating my embeddings, and this produces a vector embeddings array that contains 1024 dimensions. So I'm going to go ahead and click next and create my vector search index, and then MongoDB is going to take a couple of moments to build this index. After the build is complete, we can go ahead and use this to perform vector search. Now the problem we are going to run into is that our embedded movies collection, or to be more specific, the documents inside of it, don't currently contain the plot embedding 1024 field. So we have to go into our application and write some code to generate our vector embeddings and store them inside of MongoDB. Now the good thing about this is that when we update our document, the index will also be updated, and then we can start performing semantic search. So now let's go back to our code and implement support for generating embeddings. In order to generate vector embeddings from our .NET application, we're going to need two things. First of all, we will need a large language model that we can connect to produce the embeddings. And then we're also going to need some library that we can use to interact with this large language model. We can solve the first problem using Ollama, which allows us to run LLMs locally. So let's spend a moment to decide which model we want to use. If I navigate to the Ollama website, and then filter based on the embedding category, I can see a list of embedding models that I can use for implementing semantic search. I'm going to choose this model here, MEAI embed large, and I'm going to run it locally to produce my vector embeddings. If you have Ollama installed, you can pull this model locally using this command, and then make sure that it's running behind the scenes so that your application can connect to it. Now this specific model produces a vector embedding with 1024 dimensions, which is why I use this specific value when configuring my vector search index inside of MongoDB Atlas. If I open up the console and execute Ollama run and the name of my model, it's going to start this model behind the scenes, and my application will be able to use it to generate the vector embeddings. So now what's left is to actually connect to our large language model, and I'm going to use the Microsoft Extensions AI libraries to perform this. So let me look for Microsoft Extensions AI, and you may have to check include pre-release to be able to see these libraries. Now I want to install Microsoft Extensions AI and also Microsoft Extensions AI Ollama. So with these two libraries installed, I can implement support for generating my vector embeddings. Let me first add a configuration value, which is going to contain the URL where my large language model will be available on localhost. So by default, this is localhost and then the port 11,434. Then I'm going to update my application services to include an embedding generator, and this is going to configure an instance of an embedding generator with the generic arguments being a string representing our semantic search term that we want to generate a vector embedding for, and the second argument contains our vector embeddings using floating point numbers. This allows me to provide an actual instance of the embedding generator, and I want to use the Ollama embedding generator. I'm going to use my application settings to obtain the Ollama URL, and I also need to pass in the name of the model that I want to be using for generating my vector embeddings. The next thing I want to do is introduce a background service that's going to run when my application starts, and I'm going to call it the movie embeddings generator. I'm going to drop in the implementation, and this is going to automatically import the missing using statements. So let me walk you through the process of generating the embeddings for our movies. First, I'm going to inject a couple of services: the movie service, the Mongo client, our embedding generator, which we added to the DI container with this line of code that registers an OLlama embedding generator, and I'm also adding a logger to just log any exceptions. So what's going to happen inside of my background service is I'm going to create a database and obtain my embedded movies collection. Then I want to load the movies that I want to produce the embeddings for. For this, I'm going to just use the movie service because it already contains the required logic. And if I don't have any movies, then I can just return from this method. Otherwise, we want to extract the movies that have a plot and use that to produce the vector embeddings. Now, what's missing here is this property, the plot embedding 1024, which I want to map to the respective field inside of my document. So let me go to the movie model, and I want to introduce an additional property, which is going to be an array of floating point numbers, and I'm going to call it plot embedding 1024. I'm also going to decorate it with a bson element attribute, and let's give it the name of the field, which is plot embedding 1024, and this is the same field that we referenced inside of our vector search index. So now I can close this down and go back to the movie embeddings generator, and then let's discuss what else is inside of this method. So you can see I'm extracting movies that contain a plot, and then I'm creating a dictionary to hold my actual embeddings. And the key piece of code is this line here that calls the generate embeddings function. And this is actually surprisingly simple. I can just use the embedding generator, pass it the search term, which in the method call above is the plot of our movie, and then we are going to use this to produce our embeddings. And what I want to do is extract the actual vector array containing my floating point numbers. I'm going to add this to my dictionary and then produce a list of update operations where I'm just going to set this field in the respective document inside of my collection. And finally, I'm going to use my movies collection to perform a bulk write, and this is going to update all of my movies in one round trip. Now, you may want to implement support for batching if you are working with a large number of documents, or an alternative is using one of the integrations of MongoDB Atlas with many of the popular AI services where you can introduce a trigger when you, for example, insert a new document into a collection, and this trigger can run and execute a function. Inside of this function, you can generate your vector embeddings so that you don't have to write a background service like I'm doing here. Now, to actually run this background service, we have to register it as a hosted service. So I will say builder services add hosted service and then movie embeddings generator. So now when I start my application, I should be able to hit this breakpoint here. So let's go ahead and do that. And you can see that we hit the breakpoint inside of our background service. So now I'm going to fetch all of the movies that I want to generate the vector embeddings for. So I will place a breakpoint here and press continue. And when my query completes, I should get back around 3,500 movies. Now I want to go into the next step to demonstrate how the actual embeddings generation process works. So we're going to step into the generate embeddings method. And here you can see our search term is the plot of the movie. The embedding generator is our OLlama embedding generator instance. And when we execute this, we're going to reach out to the large language model and get back a generated embeddings instance. Now this contains some metadata about our request as well as the actual embeddings. So I'm going to extract them from this array, which you can see contains 1024 members. And if I take a look at the values, it's just floating point numbers that are the numeric representation of the plot of our movie. So I'm going to continue and add this to our dictionary. And I just want to add a breakpoint here after we generate all of the embeddings. And after about a minute, I'm going to hit my breakpoint. And you can see I have 3,403 updates that I want to apply on my MongoDB collection. The reason this is taking so long is because I'm running this model locally and I'm constrained by the capabilities of my hardware. Now, if you were using some service from OpenAI, you would get the embedding significantly faster. So I'm going to press continue. This is going to execute the update inside of MongoDB, and I'm going to jump back to my MongoDB Atlas dashboard. So I'm back in my MongoDB Atlas dashboard, and I'm going to click Browse Collections, and I want to navigate to the embedded movies. Remember that my background job has ran successfully, and if everything worked as expected, we should be able to see a new field inside of our documents called plot embedding 1024, which contains an array of 1024 floating point numbers, and this represents our vector embedding. If I go into search and vector search, we should see our vector index, and you can see that the status is ready. So our updates have propagated and the vector index was updated and now we can use it to perform vector search. If you recall, our vector search index was defined on the plot embedding 1024 field that we just introduced using our background job. And if you want to learn more about how vector search works with MongoDB Atlas, I recommend checking out the link that's going to be in the pinned comment right under this video. Now, the one thing that's left for us to do is to actually implement support for executing vector search inside of the application. So let's go back to our code and see how we can do this. In the movie embeddings generator, we already did most of the complicated work inside of the generate embeddings method. So I'm going to reuse it to implement support for vector search inside of our movie service. So let me just drop in the same method that we had before, and we have one missing dependency, which is the embedding generator. So I'm going to say private read-only I embedding generator. The generic types are going to be string, and then a vector, and then an embedding of float. And let's call this the embedding generator. And of course, I have to initialize this from the constructor. So now we can actually use this to generate the embeddings. So I'm going to update the getMovies async method, and I want to implement it like this. If the search term is null or white space, then I just want to return all of the movies inside of my collection. So I'm going to copy the query that we were executing below with an empty filter. We can also omit the filter, and in the remainder of our method, we're going to implement support for vector search. So the first thing we need is our so-called vector embeddings. So let me create a variable that is going to hold the vector embeddings, and I'm just going to call the generate embeddings method. This is an async method, so I have to await it, and I will get back my vector embeddings represented as an array of floating point numbers. Then what I have to do is to create an instance of the vector search options. So let me initialize the vector search options type. We're going to use the movie as our object model, and here I want to set a couple of properties. First, I want to configure the name of the index that we're going to use for performing the vector search. Then I want to specify if this is an exact search or not. By default, this is going to be false, which means that our vector search is going to use the ANN algorithm, which is the approximate nearest neighbor, and this is a more cost-efficient and faster way of performing vector search where we trade off precision. If we set this to true, then we're going to perform what's called an exact nearest neighbor search, and this is going to give us more precise results at the cost of performance, so it's going to be slower. So I'm going to use the approximate nearest neighbor approach, and for this I want to set the number of candidates that I want to consider when performing my vector search. Now a good approximate is somewhere around 20 times the number of results you want to get, so I can hard code this to 150 if we are returning 10 records, and that would be mostly correct, or I can take the limit parameter here and multiply that by 20. Let's say I just go with a fixed number like 200, and then how do we actually perform our vector search? Well, we have to start by calling the aggregate method, and this is going to allow us to define a pipeline. One of the available methods that we have here is vector search. The first argument is going to be the field that I want to use for my vector search. Then I'm going to pass in my embeddings, the number of results that I want to get back, and finally my vector search options. And this is all that's required to implement vector search with the native MongoDB driver inside of .NET. Now let's actually run our application and see how this works. I'm going to navigate to the client application, and I still have my semantic search query, which previously yielded no results. Now let's see what happens when we send this query now. We're going to hit the breakpoint inside of the movie service, and because the search term isn't null or white space, we're going to go ahead and produce the vector embeddings. This will give us an array of 1024 floating point numbers, and then I can initialize my vector search options and execute the vector search using MongoDB Atlas Vector Search behind the scenes. So if I press continue, we should see some results load inside of our client application, and this is how we can implement support for semantic search using MongoDB. Now, if I update my search term to say something like a movie about space exploration and hit enter, we're going to get a different result because we're going to take our search term, generate the respective vector embeddings, and then perform a vector search against the documents that we have inside of our database. If you take a look at the results, you can see that these are mostly movies about space exploration. Now, another thing that we introduced was a filter when we configured our vector search index. So let me just quickly show you how you can use this. The most correct approach would be introducing another query parameter and exposing a field on the UI where we can input this value, but I'm just going to hard code this, and remember that our filter field was the year of our document. So I can provide a filter argument in my vector search options, and I can say that I'm looking for a movie where the year is greater than or equal to 2010. So let's start the application again, and I'm going to execute the same query using the same semantic search term, and you will see that we will get back a different result set. Now our response only contains movies where the release year is 2010 or later. If we scan all of the results, you can see that this is correct. And I think this nicely demonstrates the benefits of integrating semantic search into your applications. It improves the user experience. It could also increase your user engagement and conversion rates, and by leveraging MongoDB Atlas Vector Search, we can implement some pretty complex functionality with writing a very minimal amount of code. If you are looking for a database that's going to grow with your business needs and allow you to implement AI-powered applications, I highly recommend checking out MongoDB. If you want to learn more about MongoDB Atlas Vector Search, check out the link that's going to be available in the pinned comment under this video. Now, if you enjoyed this video, I would really appreciate it if you smash the like button on your way out. Thanks again for watching, and until next time, stay awesome.